All right, this is video number 2 for section 5.3, and in this video we're gonna cover two things. Just a couple other special factoring patterns that are useful to know, and then the main focus here is going to be using factoring as a technique for solving a quadratic equation. Okay, so starting with the special patterns, there's two patterns we want to look at: perfect square trinomials as well as difference of two perfect squares. Okay, so x squared minus 12x plus 36. This is considered a perfect square trinomial because when you factor it, the two factors end up being identical. In this case, they both are x minus 6. And you could write it like that, or oftentimes we'll end up writing it as x minus 6 to the second power. Okay, so couple things that we want to kind of relate between the factored form and the expanded form. So notice that the x here is nothing more than the square root of the first term of the trinomial x squared, and then the 6 is the square root of the constant. Okay, and then probably the main thing we want to notice is that this middle term of negative 12x, it is double the product of x and negative 6. Okay, so x times negative 6 is of course negative 6x. If you double that, you get negative 12x. Okay, so in general, that means a perfect square trinomial could follow this format of a squared minus 2ab plus b squared, and it will always factor to a minus b times a minus b, or a minus b as a quantity squared. Okay, so you're simply just taking the square roots of each of these, the first term and the constant term, in order to give you the terms for the factors. Okay. Difference of two perfect squares. This is a very special situation that can come up. So the reason this is called difference of two perfect squares is because you are taking a perfect square and you are subtracting it by another perfect square. All right. This is the one binomial that still factors to binomials. Okay, so 9x squared minus 25. Notice that 9x squared is a perfect square, and then 25 is a perfect square, and there's subtraction there, so difference of perfect squares. This will factor to 3x plus 5 times 3x minus 5. And again, some relationships we want to notice here between each form. This term of 3x is the square root of the first term of 9x squared, and then this 5 is the square root of the constant. All right, and then just notice that 1 5 is positive, the other is negative. Okay, so 3x plus 5 and 3x minus 5, these are what we call conjugates of each other. So in general, if you have a difference of perfect squares in the form a squared minus b squared, we can say that this factors to a plus b times a minus b, where once again, these are conjugates of one another. Okay. All right, now moving forward, so let's talk about the zero product property, okay? Let's say I have two numbers, a and b, that are real numbers. If they are multiplying together and they equal 0, then that tells me that either a has to equal 0 or b has to equal 0, right? One or both of them have to equal 0, okay? So think of a and b, since they're multiplying together here, these are factors, right? That means this is a property that can be used to solve an equation when it's in its factored form. Okay, So what do I mean by that? Solve the following equations by factoring. X squared plus 6x equals 16. What I'm going to do is get this set equal to 0, and then I'm going to factor the left side. So x squared plus 6x plus or minus 16, that's going to factor to x plus 8 times x minus 2. Okay, and what I'm doing is I'm looking for the x values that would get this to equal out to equaling 0, right? So treat x plus 8 like a factor. You can think of it as kind of like this a here, and then treat x minus 2 like a second factor, kind of like the b. That means one or both of these has to equal 0 for us to get a true statement. So I set each factor equal to 0. Solve for x. X could equal -8 or +2. And of course, I can check those. If I plug either one of those back into the original equation, I'm going to get a true statement out. Okay. Do the exact same process for the second equation here. 4x squared equals 13x plus 12. I'm going to move everything over to the left-hand side here. And then I'm going to factor. Let's see, I'll try 4x and x to start here. Let's see, +3 and -4 should lead me to a -12 for the constant, and then outside and inside parts of FOIL will give me that -13x. So that is the correct factorization. So now by that zero product property, I set both of my factors equal to 0. Solving for x, I get -3/4 or I get +4. Okay. So this is an alternative approach to solving a quadratic equation from graphing, okay? Graphing can be kind of tedious, right? This can be a lot faster, especially when you get really strong at your factoring techniques, okay? Now, the one problem with this method is that not all equations factor, okay? Not all quadratics factor. So that's going to mean we need some other methods to be able to solve specific types of quadratic equations, okay? All right, last example. Write a quadratic equation in standard form with -2/3 and 6 as its roots. All right, so basically in this example, what we need to do is kind of work backwards from what we did in the last example, all right? So like if I had started here with x equals -3/4 and 4, those are my roots or my solutions, all right? To build the quadratic equation in standard form that they match, I'm going to put them into their related factors, which would be, again, 4x plus 3 and x minus 4, and then I multiply those out to get my standard form, okay? So back to this example, if I have a root of -2/3, then that means I should have a factor of 3x plus 2. All right, think about it. If I set 3x plus 2 equal to 0, subtract 2, divide by 3, that gives me x equals -2/3, right? And then if my other root is 6, my second factor would have to be x minus 6. I'll just set those equal to 0, and I'll multiply it out to get it in standard form. First part of FOIL, outside, inside, last. And combine your two middle terms there. And here you have a quadratic equation in standard form that has those given roots.